Picture a nationwide grid stress test. Only the grid is the solar system, and the test load is a comet from another star. In the weeks ahead, Comet 3I Atlas will force our physics and our engineering to run hot, the way a summer heat wave pushes power lines and transformers. This visitor is small at its core, yet wrapped in an atmosphere the size of a planet. It is inbound on a one-time, hyperfast pass, a live exam for everything we think we know about plasmas, magnetic fields, and how space weather threads through our technology. The clock is running. On October 29, 2025, Atlas swings through perihelion, the point where sunlight hits hardest. Near that moment, it will arc through space at about 68 kilometers per second, roughly 42 miles per second, a speed that shrinks a coast-to-coast drive into a breath. Activity has already flared far from the sun, and the numbers strain our habits. The chemistry tilts heavily toward carbon dioxide rather than water, a rare mix that creates an outsized coma and a laboratory with the knobs turned past familiar stops. We will track the lead-up, the blackout when glare blinds our best optics, and the return when the tail reappears with scars from the solar wind. Along the way, we will weigh bold ideas against careful evidence, keeping speculation in its lane and measurement at the wheel. The countdown is not drama for its own sake. It is a schedule for learning under pressure. To understand why this object matters at all, we begin with the night it was found and the math that made a smudge into a trajectory. The first alert looked ordinary. In the small hours of July 1st, 2025, the Atlas survey in Chile flagged a faint smear against the star field. Atlas is an automated lookout that sweeps the sky for anything that moves. Its algorithms catch many low streaks each night. Most prove to be asteroids on familiar paths or comets on long but bound ellipses. This one felt different as soon as the fit converged. The software pulled a trajectory that would not close. The line through the sky did not bend toward a loop. It opened outward like a sling stone leaving a sling. Astronomers call that shape a hyperbola. It is the curve you get when gravity tries and fails to keep an object. Ellipses describe orbits that return. Parabolas sit at the edge between bound and free. A hyperbola crosses a system once and then is gone. The key number is eccentricity, a measure of how far from circular the path is. Circles have eccentricity 0. Ellipses have values between 0 and 1. A parabola lands at 1. A hyperbola sits above 1. The early solution for this object came in at about 1.047. That small excess above 1 matters. It means the comet does not just visit. It passes through and never looks back. The second number that earned attention was the inclination. Most planets and many comets travel around the sun in roughly the same direction, like cars flowing with traffic on a one-way loop. Retrograde means you are moving the other way. The fit returned a tilt near 175 degrees. That is almost a full flip. The comet is slicing through the intersection against the stream, just 5 degrees shy of a perfect head-on plane. The geometry is not a curiosity. It shapes how long we see the object, from what angles, and how hard the solar wind hits its atmosphere. The velocity tells the rest of the story. Far from the sun, beyond the reach of its grip, this object would still carry about 58 kilometers per second of residual speed, roughly 36 miles per second. That is the asymptotic velocity, often called phi infinity. It is the badge an interstellar traveler wears after leaving home. Near perihelion, when sunlight and gravity squeeze the path, the speed rises to around 68 kilometers per second, about 42 miles per second. Put that against an American map. At that pace, you cross the continental United States in under 2 minutes. Coast to coast shrinks to the time it takes to pour a cup of coffee. Velocity alone does not make an object interstellar. Some long-period comets from our own cloud can dive fast. What marks an interstellar case is the combination. Eccentricity above 1. A coherent inbound direction that points to the deep sky, not to a random perturbation by a planet. A V infinity that remains high even if you turn off the sun in the model. The early follow-up did the hard check. Astronomers pulled more sightings from ATLAS frames and from other wide surveys. Each new point tightened the fit. The residuals stayed small. The parameters held steady. The hyperbola was not an artifact. It was the shape of the motion. Think of the orbit solution like plotting a long-haul route on an interstate map. You draw the line between waypoints across the country. If the dots curve back, you are planning a round trip. If the line keeps going off the edge of the page, you are passing through. The Atlas detections gave the first 2 or 3 dots. Follow-up from other telescopes added a dozen more. The line stabilized. The path cut across the planetary lanes with a steep angle and then reached for open space again. Retrograde geometry complicates more than a diagram. The planets, and most space dust, move eastward around the sun. A retrograde comet meets that flow head-on. The relative speed stack. Gas released from the nucleus expands into a wind that already feels the oncoming rush. Charged particles in the solar wind meet that expanding gas with extra punch. That is why inclination is not a footnote. It changes the exchange of momentum in the coma and tail. It changes how quickly a dust tail sweeps back and how an ion tail aligns with the interplanetary magnetic field. Eccentricity adds a second lever. A value near 1 means the object spends much of its time far from the sun, then races through the inner system on a tight schedule. Observers get a short window. Models get a stress test. Small errors in the early position fits can translate into large shifts in where the object will be when it matters. Teams do not have the luxury of a slow approach and months of practice. They have weeks to lock in pointing tables and to rehearse their tracking scripts. Now, layer in the size and the coma hints from the first photometry. The point spread looks swollen even at large distance. That means activity far from the sun. Most comets wake up inside 2 astronomical units, the distance between the Sun and Earth times 2. This object showed a measurable atmosphere well beyond that, when sunlight is still weak. Plot that on the interstate image. It is as if a car turned on its headlights while still 2 states away. Something about the surface or the volatiles makes it sensitive to gentle warming. Speed numbers invite comparison to daily experience. Highway speeds sit near 30 meters per second, about 67 miles per hour. A rifle bullet crosses the map near 1 kilometer per second, around 2,200 miles per hour. This comet at perihelion moves 68 kilometers per second. Nothing in civilian life approaches that. Our fastest spacecraft need years and gravity assists to reach similar pace. The numbers frame how hard the sun's field and radiation act on the coma. At 42 miles per second, a structure in the solar wind sweeps across the comet in moments. The plasma and the dust have little time to adjust. That favors sharp features in the tail and quick changes when a magnetic boundary arrives. Retrograde motion also shapes what Earth can see. When 2 cars pass in opposite directions on a highway, they are side by side for a blink. A prograde comet stays in our night sky longer because we share some of its sideways motion. A retrograde one cuts the path and vanishes behind the sun more quickly. The forecasts show a late October geometry where our best optical observatories have to stand down as the comet sits too close to the solar glare. That blackout, caused by the line of sight, is not a pause in physics. It is a pause in our vision. The V infinity of about 58 kilometers per second carries another meaning. It encodes a memory of where the object came from. You can trace the inbound direction back to a region of the sky and a frame moving with the local stars. It will not point to a specific system yet. The Milky Way is crowded near the center and sparse above the plane. The comet's approach vector skims those larger structures. Still, the number says that this piece of rock and ice did not form here. It spent ages between stars, wrapped in cold, then a small deflection sent it on this crossing. The orbit math records that biography without a word. The inclination near 175 degrees means the object lies almost in the same plane as the planets, but going the other way. That orientation, it increases the chance of crossing the heliospheric current sheet, the wavy surface where the sun's magnetic field flips polarity. A prograde comet at low tilt might skim a single side of that sheet. A retrograde comet with a neat near flip tilt is more likely to pierce it several times. Each crossing can wrench the ion tail and snap off pieces in what observers call disconnection events. Those are not speculative. They have been seen in many comets. What is unusual here is the tempo. With high speed and retrograde geometry, the crossings can stack into a rapid sequence. The math also informs risk assessments for tracking. Telescopes guide on stars that sit still relative to the frame during a short exposure. Fast-moving targets smear if you expose too long. The predicted on-sky rate for this object near perihelion makes long exposures impractical for fine structure. The solution is many short frames and careful stacking in the comet's reference frame. Software can align on the moving core, then subtract star streaks. All that work begins with accurate ephemerides, the tables that list where to point and how fast to track. Those tables are products of the orbit solution from July and August. The better the early math, the cleaner the later images. Even the brightness forecasts lean on orbital details. A comet brightens as it approaches the sun, because sunlight increases, and because geometry helps. When the phase angle grows large, forward scattering can make the inner haze look more intense. That can fool a naive plot. You might think gas production tripled when much of the change came from the viewing angle. Orbital elements set those angles night by night. You cannot read behavior without knowing where you stand relative to the motion. There is a human thread in these numbers. An Atlas night operator watches a dashboard fill. A scientist on call checks a set of residuals against a grid of previous fits. A minor planet center circulates a designation. Dozens of small instruments spin up for confirmation shots. The data pour into the solvers that turn streaks into elements. Most nights end with a tidy update and an unremarkable orbit. This one ended with a hyperbola and a retrograde tilt so sharp that you could feel the room wake up. Precision matters, yet communication matters more. Numbers only help if people can grasp their scale. That is why we translate 68 kilometers per second into 42 miles per second. That is why we compare a near 1 eccentricity to a door that will not swing shut. That is why retrograde earns the image of a wrong-way lane on a cloverleaf. The goal is not to dress the math. It is to make the math usable by anyone who carries a mental map of highways and coasts. Orbit mechanics make no promises about what a comet is made of. They only tell you how and when it moves. The early hints of activity at large distance suggest unusual surface chemistry or structure. The velocity and geometry tell us the stage will be windy and bright near late October. The rest depends on what boils, what vents, and how gas and dust respond to heat. To see why, the inner atmosphere of this object looks oversized, and why its glow started so far out, we must step from motion to material. The first deep look at ATLAS did not return the usual recipe. Most comets carry water as the main volatile, with carbon dioxide and carbon monoxide as backup players. Here, the mix flips. Spectra point to a carbon dioxide to water ratio near 8:1. Say that out loud, and it lands with weight. For every cup of water vapor, about 8 cups of carbon dioxide leave the surface. That ratio alone explains why the coma swelled early and far from the sun. Carbon dioxide turns to gas at colder temperatures than water. It wakes up when sunlight is still weak and the solar distance is large. Activity that begins far out lays the groundwork for everything that follows. Scale the ingredients to something you can picture. The solid core is less than 5.6 kilometers across, roughly 3.5 miles. That is smaller than many towns and shorter than a morning run along a beach boardwalk. Yet the coma, the thin atmosphere around the nucleus, reaches hundreds of thousands of kilometers, on the order of 200,000 miles or more. A body the size of a small city is generating a cloud larger than Earth's distance to the moon divided by 2. The numbers feel mismatched until you remember that a coma is not dense air. It is a spray so thin that a breath would hold more molecules than a whole cubic yard of that cloud. Thin does not mean small. Thin can extend very far when the source runs long enough and sunlight drives the flow. Why does carbon dioxide dominate, and why so early? The answer starts with the properties of ice. Water ice holds tight until it warms well above the deep cold of space. Carbon dioxide ice is looser. It sublimates, meaning it jumps from solid to gas without a liquid phase, at a lower temperature. If the nucleus stores carbon dioxide near its surface, a weak trickle of heat can spark a steady flow. That flow drags dust grains from the pores and lifts them into sunlight. Dust absorbs light and warms, which can free still more gas. The process is a loop, not a single push. Start the loop far from the sun, and you enjoy a long runway before the inner system. There is also structure to consider. A comet is not a smooth stone. It is a fragile pile of grains and ices, riddled with voids. The topmost layer can bake into a crust that slows water. Carbon dioxide below that crust can find channels that reach daylight sooner. When those channels open, they act like vents in a house on a cold morning. The warmest air finds the path and accelerates out. The plume expands and chills. Gas spreads and dust follows. The coma grows without a need for large pressure underground. You get jets and fans that flicker as the nucleus spins and as sunlight shifts across its face. Think of the nucleus as a giant coffee percolator for a moment, the section's lone metaphor. The sun is the warming plate. Heat seeps through a packed bed of grains. Carbon dioxide is the steam that finds paths up through the grounds. Small bubbles link into larger channels. The top tightens as some grains sinter into a crust. A few vents punch through and carry aroma into the room. You do not need a huge kettle to fill the kitchen with smell. You need steady heat, a porous bed, and a handful of open spouts. Atlas behaves the same way, only the kitchen is a slice of space, and the aroma is a faint glow at the edge of vision. The size paradox softens further once you count surface to volume. Small bodies cool and warm quickly. They present a lot of surface for their mass, which means sunlight has many square meters to work with. If the crust is thin and the pores are open, a small patch of sunlight can support a persistent plume. Multiply by many patches and you build a global coma from a modest core. The coma's reach then depends on the balance between release and loss. Photons break molecules. Solar wind pushes ions down a tail. Gravity barely tugs on anything. As long as the nucleus keeps feeding the flow, the cloud persists and expands. Energy is the other balance you can grasp without equations. Sunlight is weak far out and strong near in. The power per square meter drops fast with distance. Yet, carbon dioxide needs only a smaller nudge than water to fly. At 3 astronomical units, sunlight is cool by Earth standards, like a bright day in late winter. In numbers, it is about 1/9 of what you feel at Earth's orbit. In Fahrenheit, it is not about air temperature, but you can imagine a reflective surface warming from near 100 below to near 20 below as the day grows. That gap is enough to kick carbon dioxide loose in a shadowed pore while water waits deeper in. As the comet drifts inward, the power climbs. The loops speed up. Dust darkens the surface and absorbs even more light. The machine runs hotter on the same plan. You can ask how the carbon dioxide got there in the first place. Two paths offer reasonable answers. One is birth. The comet formed in a region of its home disk where carbon dioxide was abundant and water ice was buried deeper or bound into different minerals. The other is processing. Time in interstellar space can alter the top layers through radiation. It can compact some pores, open others, and segregate volatiles into pockets. Both are plausible. Both end with a surface that favors carbon dioxide release under weak heat. The current data do not choose between them. They do not need to yet. The order of operations at the surface is clear, even if the deep story takes more work. The 8-to-1 ratio echoes in the spectrum. Carbon dioxide has strong fingerprints in the infrared. Water has its own. When astronomers see the carbon dioxide bands swell, while the water bands lag, they know the mix. They also watch for carbon monoxide, which turns on even earlier than carbon dioxide. If carbon monoxide stays faint, the case grows stronger that carbon dioxide holds the key. The coma then becomes a map in motion. Where the carbon dioxide glows brightest shows where vents face the sun. Where water finally rises later shows how deep the water reservoir sits and how the crust evolves. Dust is a second witness. Carbon dioxide jets can carry fine grains more easily than water jets at the same power. Fine grains scatter sunlight in a way that makes the inner haze seem smooth. Coarser grains create a more textured look, like a faint lawn of specks around the core. Early images of ATLAS favor a soft inner profile with a long taper. That supports the idea that fine dust dominates and that vents run steady rather than explosive. If a big outburst were common, you would expect sharp shells and fast brightening curves. Those curves have not ruled the light so far. Radiation pressure sorts dust by size once it leaves the core. Small grains feel more push per mass than large ones. Over hours, the dust fan bends and separates. The ion tail does not care about radiation pressure. It follows magnetic fields and points away from the sun like a windsock. The chemical mix sets how much material enters each channel. A carbon dioxide heavy coma often shows a bold ion tail because ionization is brisk. A water-heavy coma can favor dust if water dominates late and lifts coarser grains. Atlas will likely carry both flags, yet the early carbon dioxide stream sets the tone. Close to perihelion, the energy budget can run tight. Carbon dioxide pours out. Some sunlight gets lost to heating dust that does not carry gas. Some energy leaves in the form of escaping molecules. Some goes into warming the crust. Observers will look for signs that the system reaches a limit. A coma can only grow so bright near the sun before geometry blinds the view. A nucleus can only shed so much before pits deepen or rims slump. Day by day, photometry will show whether the output plateaus or spikes. If it holds steady through the bright days, the vents are robust. If it stutters, structural change is underway. None of this demands pressure like a sealed pot. The flows run at low, absolute pressure, more like a breeze in a dry canyon than a storm. That is why even a small nucleus can feed a large volume. Molecules have long paths between collisions. They ballistically expand until sunlight breaks them or fields steer them. The coma tells a story written one molecule at a time across a vast room. The size paradox also hides a gift for modelers. A small nucleus means a shorter rotation period is likely. Faster spin cycles modulate jets on timescales accessible in a night. You can watch a vent rotate into and out of sunlight and watch the inner coma breathe with it. That breathing encodes the map of active areas. If you combine the light curve with spectra, you can tell whether a bright patch is bright from dust, gas, or both. The mix of carbon dioxide and water sets the tempo of that breathing. Carbon dioxide reacts faster to sunlight changes. Water lags and smooths. Reading the lag puts numbers on depth and on thermal inertia. The tendency to hold heat. There is a caution to state. An 8-to-1 ratio is an average across the footprint of an instrument and across time. Real surfaces are patchy. Some areas could be almost pure carbon dioxide release. Others could be water-rich. When teams say the comet is carbon dioxide dominated, they mean the overall budget leans that way. Local vents will still surprise. A bright water jet could flare near perihelion on a rim that finally cracked. A carbon dioxide vent could choke where dust fell back and sealed pores. These swings do not erase the headline. They add texture. A carbon dioxide-led coma at solar maximum is an amplifier. It makes the ion processes louder and earlier. It paints magnetic structures with brighter strokes. It offers more hours of readable tail under modest light. It also means the comet spends more time in a state where non-water chemistry drives the show. That helps separate plasma physics from water-specific quirks. In a sense, the chemistry shock simplifies the space physics by turning up the signal. By late September, the carbon dioxide machine is humming. The dust fan is broad, and the nucleus is a busy percolator under a sky that grows harsher by the day. The next piece is how that sky behaves when the sun is near its active peak and the solar wind carries structure like weather fronts rolling across a continent. Start with the simplest picture. The sun blows a constant outflow called the solar wind. It is a thin gas of charged particles. It carries the sun's magnetic field with it. A comet drifts into this flow and begins to breathe gas and dust. Light from the sun knocks electrons off some molecules. That process is photoionization. The result is a cloud of ions, electrons, and dust grains in the same space. Physicists call that mix a dusty plasma. It behaves like a fluid made of electricity and motion. Now, bring the calendar into view. The sun runs on an 11-year cycle. Near the peak, called solar maximum, the wind is gusty. Magnetic fields flip and fold. Huge eruptions, called coronal mass ejections, lift off and sweep through the inner system. Each one is a bubble of magnetized plasma moving hundreds of miles per second. The background field that threads space is not steady. It is a patchwork that shifts day by day. Magnetic field lines are a map for charged particles. They are not ropes, but they guide motion. A free ion feels a force when it tries to cut across the field. It spirals around the line and drifts along it. Gas in the comet's coma turns into ions under sunlight. The solar wind picks those ions up. It pulls them into an ion tail that points away from the sun. This is not a guess. It is observed in comet after comet. Photographs and spectra show sharp blue-toned ion tails that aim anti-sunward. The direction can swing when the magnetic field swings. The tail is a visible compass. Dust does not obey the same rules. Dust grains can charge up, but they carry more mass. They feel sunlight as pressure, like a breeze on a flag. Radiation pressure pushes small grains farther than big grains. That creates a broad dust tail that curves. The curve points back toward the orbit path. At times, the dust also joins the plasma dance. Charged grains can respond to field changes, especially the smallest sizes. When that happens, dusty plasma physics takes the stage. This blend is trickier than pure gas. It can form waves and clumps that a simple model will miss. We have images that hint at this behavior. We also have lab studies. The full effect in a giant comet coma remains an active question. Think of the heliosphere as a river basin for a moment. The single metaphor here. The solar wind is the current. The magnetic field lines are the channels within the flow. The heliospheric current sheet, or HCS, is like a wide, meandering boundary between two branches of the river that flow with opposite spin. On one side, the magnetic field points away from the sun. On the other side, it points toward the sun. The HCS ripples as the sun rotates. The ripples spread outward like slow waves. A comet that crosses this boundary moves from one branch into the other. The ion tail will often twist or kink as the field flips sign. We have watched these kinks many times. They are not speculation. They are part of the record. Photoionization is the engine that primes the tail. Ultraviolet light hits a neutral molecule and frees an electron. The leftover ion is now visible to magnetic forces. That change happens in fractions of a second under bright sun. Near solar maximum, the ultraviolet output is stronger on average. Ion creation rates rise. More ions mean a brighter ion tail and a bigger footprint for the solar wind to push. Observers can measure the rate by watching specific spectral lines. The numbers tie back to how quickly the neutral coma turns into plasma. Another pathway creates energetic ions without light alone. The solar wind contains heavy ions from the sun's hot corona. When those ions hit neutral gas near the comet, they can steal an electron in a process called charge exchange. The new ions move slower. They radiate X-rays as they settle into new states. Telescopes have seen this X-ray glow at several comets. That is an observation, not a theory. The glow maps regions where the wind first meets dense gas. It often sits on the sunward side of the coma. When a coronal mass ejection arrives, the glow can surge. That surge is also observed. Coronal mass ejections, or CME, cess matter because they carry strong fields and dense plasma. When a CME encounters the comet, pressure increases. Field lines drape more tightly around the coma. The standoff distance, which is the place where the wind slows and diverts, can move inward. If the CME field points in a direction that fights the comet's induced field, magnetic reconnection can occur. Reconnection is the breaking and rapid rejoining of field lines. It converts magnetic energy into particle motion and heat. In comet tails, reconnection can snap off a segment and send it drifting away. Those tail disconnection events are well documented. They show up as sudden gaps that travel down the tail. The HCS adds a rhythm to these events. As the comet crosses from one magnetic polarity to the other, the draped field around the coma must reconfigure. The ion tail responds. It can twist, fold, or split. The number of crossings depends on the path. Atlas travels retrograde at a tilt near 175 degrees. That geometry favors multiple crossings near the inner system. The speed is high. Changes can arrive in a tight sequence. The plasma around Atlas will have to adapt on short timescales. Observers should expect a lively tail. Magnetohydrodynamics, or MHD, is the standard language for large-scale plasma. It treats the plasma like a conducting fluid. It follows how mass, momentum, and magnetic fields evolve. MHD has explained many comet features. It gets the broad draping of field lines right. It predicts a bow shock in stronger cases and a pile-up region where the wind slows. It predicts the ion tail alignment with the field. Yet even good MHD has limits. It can smear out fine structures that depend on particle-level physics. It can miss how charged dust grains alter conductance. It can lag when reconnection goes fast in thin sheets. At solar maximum, the flow may leave the comfort zone that simple MHD handles. The river in our metaphor switches banks more often. Eddies form and collide. CMES layer on top of the background. Thin current sheets form in the draped field. In those sheets, reconnection can trigger on scales too small for a coarse model. The result is bursts and waves that race through the tail faster than the fluid picture suggests. Some of these bursts have been observed as sudden brightness changes or as waves in radio data. Others are inferred. This is where theory and simulation try to catch up with the details in the sky. Dusty plasma effects add another layer. Charged grains can soak up electrons and change the balance of charges. They can act like moving capacitors in a circuit. They can damp some waves and amplify others. In a carbon dioxide-rich coma, like Atlas, fine dust production is strong. That supports the idea that dusty plasma will matter. We have indirect signs in light curves and in the shape of near-nucleus halos. We also have reasoned models from laboratory studies. Direct, in situ measurements would confirm the scale of the effect, but no such probe flies with ATLAS. For now, we label dusty plasma impacts as likely and important, with details under study. Pick up the thread of reconnection again. The term sounds abstract. In practice, it is a release valve. Field lines stretched tight by the wind can snap and rearrange. Energy stored in the field pours into particles. At Earth, reconnection drives auroras and space storms. In a comet tail, it can cut a ribbon of plasma and send it away. In some sequences, a CME sets the stage and the HCS crossing pulls the trigger. Photometric time series show the tail break. Then a new tail grows in the updated field direction. That sequence is observed. The exact trigger at small scale is still debated. Some teams favor turbulent cascades. Others favor thin sheet instability. The science is careful about this distinction. What about radio signatures? A plasma can support waves that make radio noise. As pickup ions join the flow, they create oscillations. Arrays on Earth have detected structured radio patterns near comets. These structures align in time with optical changes. That alignment is observed. The detailed link from wave type to tail feature is still a theory space. Researchers test candidate models against timing and frequency. They tune the models until the output tracks the data. When a pattern holds across multiple events, confidence grows. Until then, we mark radio structure as observation with interpretation in progress. Photoionization rates and dust output also sculpt the so-called diamagnetic cavity near the nucleus. This is a region where the magnetic field is weak or excluded by dense outflow. The cavity size depends on gas production and wind pressure. A surge in production can push the cavity outward. A strong wind can compress it. Remote sensing can estimate cavity scale from forbidden line emission and from how the ion tail starts. It is an indirect measure. Spacecraft flybys, in the past, have confirmed cavity physics at other comets. With Atlas, we will infer rather than touch. The method is tested, but each case adds nuance. The HCS has a large-scale pattern, yet the wind on top of it is patchy. High-speed streams from coronal holes can follow slow wind. The interface carries sharp gradients. When such a stream hits a comet, the ion tail can ripple. The ripple travels along the tail at a speed set by the local magnetic tension. The pattern is delicate and short-lived. You need cadence and luck to catch it. Solar maximum raises the odds of both the forcing and the detection because signals are larger and teams are watching. Reports of ripples will be observations when they match coordinated data. Explanations for the ripple shape will be theory until a full chain fits. Electric fields also play a role. As ions stream, they set up potentials across the coma. Dust grains charge and discharge. Electrons move swiftly and cool or heat the plasma. Simple models use ambipolar fields to keep charges in balance. Reality may be more jagged. Patches of high ionization will form near hot vents. Shadows will cool pockets. Electric drifts can steer small dust in ways that alter near-nucleus brightness. Some of these effects are observable as asymmetries that rotate with the nucleus. Others will hide under distance and glare. Atlas offers a chance to watch them because carbon dioxide drives structure at larger distances where glare is lower. None of this requires exotic physics. Plasmas couple fields and flows. They support waves and instabilities. They respond to boundaries like the HCS and to sudden pushes like CMES. They convert stored magnetic energy into motion through reconnection. Every step has been observed in pieces across comets, planets, and the sun. What is rare is the combination we face now. A small, active nucleus with a carbon dioxide-rich coma. A retrograde path that cuts the HCS. A peak in solar activity that throws frequent CMES. A speed that compresses events into hours. The plasma here will not be gentle. As we move toward October, geometry turns from a backdrop into a lead actor, because where we stand in the river sets what our instruments can see and when they must go dark. The calendar for ATEL AS reads like tight stage cues. The lighting changes as the comet moves, and our line of sight dictates what the instruments can do. On October 3rd, it brushes past Mars by interplanetary standards. On October 29th, it reaches perihelion. In early November, the path tilts near Venus. By mid-December, Earth gets a better look as the glare fades. In 2026, the track drifts toward Jupiter's realm at a long standoff. Each waypoint changes the angles. Each angle changes what physics we can read. Start with Mars, because the red planet is a useful balcony seat. A close pass in early October offers geometry that Earth lacks. Mars orbiter cameras can stare into a darker sky with longer, steadier looks. The comet will fill a larger fraction of their pixels. The ion tail will cut a cleaner silhouette against space. On those days, Earth faces strong evening twilight. Ground telescopes will fight low altitude, thick air, and scattered light. Mars will watch the same coma under different lighting. That difference is pure signal. With 2 vantage points, we can separate a real change from a trick of the angle. Perihelion sits at the center of the story and the center of our limits. As October 29th approaches, the solar elongation shrinks. That is the angle between the comet and the sun in our sky. Small elongation means glare. It means detectors that saturate even in short exposures. It means pointing rules that forbid some moves. Hubble has a strict sun avoidance zone. It cannot risk staring too near the solar limb. Webb cannot point anywhere. The sun shield would fail to protect its mirrors. The comet can be bright and busy, yet the best eyes must look away. The physics keep running. The room lights just turn up too high for a camera. Ground observatories face the same geometry with extra trouble. The atmosphere scatters sunlight across the field. Air mass grows when a target sits low. Turbulence adds blur. Even with careful tracking, the inner coma becomes a smudge inside a flood. You can catch the tail if it stretches into a darker patch, but the near nucleus region goes white. That is not a malfunction. It is the expected outcome of small elongation in solar maximum glare. The blackout window is a practical label for a period when pointing and physics pull in opposite directions. Not all sensors go blind at once. Radio arrays can listen through twilight and daylight. The solar disk is loud at some bands, but careful frequency choices and spatial filtering can isolate the comet's radio waves. When the ion tail shakes, it can emit structured radio patterns. Arrays can catch those even when optics cannot see fine structure. Solar far-side imagers and coronagraphs can help too. They reject direct sunlight and watch the immediate region around the sun. If the tail extends inward enough, a coronagraph may record its inner edge. Those images will be coarse, but a coarse outline at the right time can still pin down a magnetic flip. The angle at which sunlight strikes the dust matters as much as raw brightness. Phase angle is the Sun-Comet observer angle. Large phase angles near perihelion produce strong forward scattering. Dust grains throw more light toward us when we stand almost behind the sun. That forward enhancement can make the inner haze glow like a halo. It is not a sudden surge in gas production. It is geometry bending the light our way. Observers must correct for this effect, or they will confuse lighting with chemistry. The correction uses orbit elements and a scattering law. Get the angles right, and the light curve becomes honest again. Mars to Earth parallax is a tool during the October weeks. If Mars cameras and Earth telescopes take synchronized shots, we can measure small shifts in tail features. Those shifts decode distance and speed across the tail. A kink moving down the ion tail at a known rate constrains the local magnetic tension. That number feeds models of reconnection and current sheet crossings. Parallax also helps fix the comet's precise path when the glare grows. Every added constraint reduces pointing errors in the recovery phase. After perihelion, the geometry improves day by day. Solar elongation opens. The comet rises higher after sunset for Northern Hemisphere observers. Air mass drops. Scattering eases. Phase angle shrinks, so forward scattering fades. The dust fan looks more honest. The ion tail takes a steadier line. That is when mid-latitude sites in the United States can resume routine cadence. Short exposures, frequent stacks, and a fixed field can yield movies of the tail's daily evolution. The glare months are not lost time. They are a tight turn in the road before a straighter run. The early November tilt near Venus is a curiosity rather than a close pass. It changes the sight lines from inter-system spacecraft. Some Venus orbiters carry plasma instruments and cameras that can opportunistically scan the tail. The value is timing and context. If a coronal mass ejection leaves the sun near that date, the Venus Vantage might record the first brush. That gives Earth teams a heads up for what to expect as the same structure sweeps past the comet and then reaches our own magnetic bubble days later. By mid-December, The comet's elongation gives ground telescopes the breathing room they need. The tail will be long and faint. The inner coma will be smaller in angle. That is fine. The science shifts from glare management to structure tracking. Photometry becomes more reliable because forward scattering no longer biases the line of sight. Spectra become easier to calibrate against the dark sky. Amateurs can contribute steady, well-labeled images from suburban sites. Professionals can put narrowband filters on the core and measure how the carbon dioxide to water balance evolves after the peak. Jupiter in 2026 is the final marker on this list. It is not a rendezvous. It is a reminder that geometry keeps helping long after the headlines fade. Jupiter's location will shape background plasma streams in the outer system. The comet's tail will be diffuse and faint by then. Yet the large-scale solar wind still leaves fingerprints on dust fans and ion drifts. Long baseline radio coverage may catch low-frequency waves that reflect the slower wind far out. Geometry again sets which instruments have a fair chance. Instrument teams plan around these angles months in advance. Hubble staff build pointing tables that respect sun and Earth limb constraints. Webb schedulers plan windows when the sun shield can shade the line. Ground observatories mark nights when the comet clears trees and domes and sits at useful altitude. Radio arrays assign dynamic blocks that can move with the comet's changing right ascension. Even the data pipeline must think geometrically. Software needs the correct angles to subtract scattered light, to set aperture sizes in kilometers, and to index stacks by the right frames. The blackout is not a total silence. It is a shift in who speaks and how loudly. When optics step back, radio and X-ray take more weight. When Earth cannot point, Mars or Venus can take a turn. When Hubble and Webb pause, coronagraphs and helioseismology imagers offer context. The chain is only as strong as the links we test in calm times. That is why rehearsal with fast asteroids and with past comets pays off now. Teams learn to move data across bands and to switch cadence without debate. The phase of poor geometry also tests patience and judgment. A rushed claim can follow from a brightening that is only forward scattering. A false lull can follow from a drop in contrast rather than a drop in gas. The cure is to lean on angles, not feelings. If the elongation is tight, assume glare is cheating your eyes. If the phase angle is large, discount dust brightness before calling a surge. If the ion tail swings while the current sheet crossing is due, favor the field change over new chemistry. Discipline keeps the narrative clean. United States observers sit at mid-latitudes with weather that can be kind or cruel in autumn. The Southwest has clearer skies and long twilights. The East fights clouds but gains darker air faster after sunset. The Midwest splits the difference. Alaska will trade altitude for long darkness. Hawaii and Puerto Rico offer stable air for infrared and radio. The map matters. If teams coordinate, they can stitch a near-continuous record through the weeks when a single site would miss hours to clouds or horizon. A special note belongs to saturation and persistence. Some detectors remember bright light for minutes. If you swing past the sun to catch the comet, ghost images can contaminate the field. Planning mitigates this. Observers can schedule a safe detour, then dark frames, then the target. Software can model the ghosts and subtract them. But awareness is the first step. The blackout is not only about geometry. It is about protecting instruments and data quality when glare and heat creep into the system. Timing folds into model validation. The Mars window tells us how the coma breathes before the glare. The blackout forces reliance on radio and X-ray, which respond more directly to plasma dynamics. The December return lets us check how the tail healed after reconnection cuts. The sequence gives a before, during, and after. With that sequence, we can ask models to do more than paint a picture. We can ask them to predict the changes between the frames. In short, geometry is the quiet master of this campaign. It decides who gets a turn, which sensors shine, and which blind spots we must accept. If we respect the angles and plan for the blackout, we will pull a clean thread through a busy sky. With the schedule set by orbits and the view filtered by glare, the next challenge moves from where and when to how our equations behave when the plasma does not play by easy rules. Most of our space weather playbook rests on magnetohydrodynamics. MHD treats a plasma like a single conducting fluid guided by magnetic fields. It averages over the paths of individual ions and electrons. That average makes the math tractable and the pictures smooth. It works well when changes are slow and structures are large. It struggles when the system becomes quick, thin, and layered. Atlas pushes it into that hard corner. Start with scale. The coma stretches hundreds of thousands of kilometers. The nucleus is a few kilometers wide. The ion tail can run millions of kilometers. Fine dust grains measure microns across. Solar wind structures sweep by in minutes near perihelion. A single model would need to connect all those scales at once. That is like asking one map to show a backyard fence and a coast-to-coast route with equal clarity. If you zoom out, the fence disappears. If you zoom in, the highway becomes a thin line with no traffic. Timescale stacks on top of size. Electrons respond in microseconds. Ions take longer. Dust drifts even slower. The wind can flip its magnetic polarity across the heliospheric current sheet in less than an hour. A coronal mass ejection can lift pressure in a few minutes. A jet on the nucleus can brighten along a rotation curve. MHD usually picks a single clock and a single speed for the fluid as a whole. It blends fast and slow into one. Under calm conditions, that blend is fine. Under Atlas conditions, the blend hides the very dynamics we hope to study. Composition is the third wedge. Atlas carries a carbon dioxide-rich gas and a strong load of fine dust. Electrons and ions move freely. Dust grains hold charge and mass. They soak up electrons and then release them. They carry momentum in a way gas cannot. Classic MHD does not have a place to track charged sand grains that behave like slow capacitors. A multi-fluid model can add a dust component and a separate charge balance. That change adds equations and parameters. Each new term needs a value. Many of those values are not measured directly. They are inferred with error bars. A good model admits those uncertainties. A poor one hides them in constants that look precise. Reconnection exposes another edge. In MHD, magnetic reconnection happens because a small resistivity allows field lines to break and rejoin. Real plasmas often reconnect much faster than that simple picture allows. Thin current sheets form. Electrons and ions decouple. Waves carry energy away. Hall effects become important. The correct description is kinetic rather than fluid. Kinetic means you follow particle distributions, not just bulk speeds. That requires far more computation. It also requires input that observations may not supply. Atlas will drive reconnection in a tail that crosses the HCS and meets CMES. A pure MHD code can draw the broad shape. It will likely miss the pace and the burstiness. That gap is not a failure of effort. It is a sign that the physics sits beyond the model class. Nonlinearity makes the gap tangible. Imagine a sound system at a concert. The single metaphor for this section. A singer's voice feeds a microphone. The mic drives an amplifier. The speaker pushes air back into the mic. If the gain is low, the loop is stable. The music is clear. If the gain creeps up, a squeal erupts. A tiny shift creates a loud, sharp tone. The room and the gear feed back on themselves. Plasmas do the same. New ions load the field. The loaded field bends. The bend changes the pickup rate. The pickup changes the load. A smooth flow jumps into a wave. MHD, with gentle parameters, misses the squeal. High-gain physics in a thin sheet does not. Turbulence plays a quiet but relentless role. The solar wind is not a steady stream. It holds eddies within eddies. Energy cascades from large scales to small. At the small end, particles heat and waves damp. MHD captures the cascade down to the grid size. Below that size, the code has to fake it with an effective viscosity or resistivity. Those choices change how and when energy shows up as heat or motion near the comet. Under simple flows, the choices do not matter much. Near Atlas at solar maximum, they do. An eddy that survives to the tailbase might set the timing of a disconnection. One that dies early might not. Numerical limits sharpen all of this. A computer solves MHD by cutting space into cells and stepping time forward in small jumps. Halve the cell size, and you often must take 4 times as many steps. Triple the cell size, and you can run faster, but lose detail. The coma and tail require very fine cells near the nucleus and coarser ones far out. Adaptive meshes can help by refining the grid where gradients are steep. They cannot fix missing physics. If reconnection depends on scales 1,000 times smaller than your smallest cell, you will not get the right trigger. You will paint a reconnection that looks pretty and arrives at the wrong hour. Hybrid and particle and cell methods go deeper. A hybrid model treats ions as particles and electrons as a fluid. A particle in cell model treats both as particles. These methods respect kinetic effects that MHD erases. They can capture fast reconnection and waves that ride on particle drifts. They also cost far more. Covering a coma with such a code is often out of reach. The compromise is to carve out a patch near a thin current sheet and simulate only that part. Then you couple the patch to an MHD model for the rest. The seam between the two models is a source of uncertainty. It must pass energy and momentum cleanly. It rarely does on the first try. Parameters set the stage for success or failure. Outgassing rates, dust-to-gas ratios, ionization times, and background wind conditions all matter. If you set them wrong, the right model will still miss the behavior. If you set them right, but the model class is wrong, the fit will still look good for the wrong reason. That is why we need data that pin more than brightness. We need standoff distances as a function of time. We need tail axis angles at known current sheet crossings. We need radio frequencies that track pickup ion waves. Each number cuts the space of plausible models. Nonlinearity defeats comfort in another way. You can build two models with tiny differences in one knob. Under calm input, their outputs stay close. Under a fast CME, one model might show a smooth kink and recovery. The other might show a snap and a gap. Which one matches the sky? Depends on details you did not measure. That is why honest ensembles matter. An ensemble is a set of runs with varied inputs within error bars. The spread of the ensemble tells you the confidence band on a forecast. Under Atlas conditions, that band may be wide. A wide band is not a flaw. It is a true statement about what you do not know. Thought experiments help show why feedback wins. Picture a slab of carbon dioxide ice under a thin crust. Sunlight rises by a small amount. Gas flow increases. Dust lifts. The surface darkens. The darker patch absorbs more light. Gas flow jumps again. The flow enlarges a pore and lowers local pressure. More ice sublimates. The loop continues until the rim collapses and chokes the vent. The light suddenly drops. The plasma footprint shifts. Reconnection starts in a slightly new place. A model that averages the surface into one neat layer will smooth over the loop. It will miss the quick jump and the sudden fall. Now, add the HCS. The comet crosses from one magnetic polarity into the other. The draped field around the coma flips and tightens. The ion tail twists. In the same hour, a CME flank raises pressure. The standoff distance moves inward. Two independent pushes arrive together. Their order and timing decide whether the tail sheds a long segment or only a small curl. MHD can show both outcomes. Which one occurs depends on actual timing that may differ by minutes. Without rapid cadence, you will match one event by luck and miss the logic. Some proposed fixes will sound familiar from other fields. Subgrid models try to capture small-scale effects with tuned terms that stand in for missing physics. In weather models, these terms represent cloud microphysics. In comet models, they can represent fast reconnection and dust charging. The tuning relies on data. Atlas will provide part of that data if we record the right things at the right times. Until then, subgrid choices are educated guesses. We should label them as such. Hall MHD includes an extra term that accounts for how electrons slip past ions on short scales. It improves reconnection rates and wave behavior. It still does not track distributions. It is a better fluid model, not a kinetic one. Hybrid codes are a step beyond and can live in the space between realism and cost. They are promising for thin tail sheets that drive disconnections. They still need strong boundary conditions from larger scale MHD. Speculation springs from structured radio patterns that some arrays see. The patterns show timing and frequencies that line up with ion pickup physics. The safe reading is that the tail supports waves that we can hear as radio noise. A bolder reading suggests system-wide coordination across large distances. That claim needs more proof. It also needs a clean chain from cause to effect. For now, we mark the radio structure as a real observation with several active interpretations. We prefer natural self-organization in a complex plasma until evidence forces a jump. Another speculative branch points to electromagnetic coupling across the inner system. The idea is that disturbances near the comet could influence other regions along magnetic field lines. Similar couplings exist near planets and in the solar wind itself. Extending them to a comet at these scales remains a stretch without direct evidence. If teams find synchronized changes at multiple spacecraft that line up with comet events and with field connectivity, the case will strengthen. Until then, we keep these ideas in the column labeled interesting and unproven. Computation sets hidden limits on ambition. A full run that resolves a diamagnetic cavity and a draped field out to millions of kilometers would need billions of cells. Each time step would be tiny to keep the code stable. A day of comet time could cost weeks of wall time on a large cluster. That expense forces choices. You pick a smaller domain, a coarser grid, or a reduced physics set. You accept that your picture is a sketch, not a photograph. That is not defeat. It is craft. You choose the sketch that captures what your data can distinguish. The hardest part for experts is to say, "I do not know," and then quantify it. In public, certainty sells. In science, certainty is earned. With Atlas, the honest stance is clear. MHD will draw the big shapes and get the broad timing right on quiet days. Hybrid and kinetic patches will explain specific bursts and cuts. Both will depend on inputs, with error bars. Ensembles will bracket the range of outcomes. Some events will fall outside the bracket. When that happens, the fix will not be a press release. It will be a parameter audit, a grid test, and a new run. Why spend so much care on the limits? Because the next step is to build the observing plan that feeds models the numbers they need. We must design tracking, exposure, and cadence to serve the physics, not the other way around. We must prepare to guide on a moving target, pull structure from glare, and pass radio and optical timing back and forth without delay. The models will improve only as fast as the measurements grow sharper, and that takes engineering and discipline more than rhetoric. The first challenge is motion. Atlas will slide across the sky faster than most telescopes prefer. Track too slowly, and the comet blurs. Track on the comet, and the stars streak into lines. Both outcomes throw away detail. The cure is cadence. Observers use many short exposures and align them in software on the moving core. That choice preserves inner structure while turning background stars into smooth trails that are easier to subtract. It also demands precise ephemerides and fast guiding loops that do not wander. On a good night, the work feels like a relay team. Hawaii takes the baton at dusk in the Pacific. Arizona and New Mexico hold the pace through midnight. Texas and the Midwest grab before dawn. Puerto Rico and the East Coast cover early mornings and radio bands. Each handoff keeps the non-stop rhythm while weather plays defense. No single site can guarantee a clear night in October. A chain of sites can guarantee a clear hour somewhere at any time. Star streaks are not just a cosmetic issue. They confuse photometry when the coma sits on a crowded field. A background giant can fake a bright patch in the tail. Teams fight back with difference imaging. They build a clean reference field from earlier nights. They subtract that reference from each comet frame. What remains is the coma and the tail. The method is old in supernova work. It is now standard for fast comets under glare. Guiding brings its own traps. Many systems lock on a guide star and adjust the mount to hold that star fixed. If the comet is the target, that plan fails. The solution is non-sidereal tracking at the comet's rate and angle. Not every facility has that mode. Some add it through firmware updates and scripts. Others fake it by taking rapid short images and nudging between frames. Either way, the operator must trust a moving lock rather than a steady one. That is a skill you learn before the rush, not during it. Exposure time is the next lever. Long frames burn in sunlight even when the comet sits far from the sun. Short frames raise red noise. The compromise is often a burst of 1 second to 5 second shots repeated for minutes. Software stacks them in the comet frame and rejects cosmic rays and satellites. The stacks behave like a single longer exposure without the bloom. They also give timestamps fine enough to catch fast changes near the tail base. Spectroscopy raises the bar. A slit has to sit on the tiny inner coma while the nucleus moves. Acquisition requires a dance. First center the comet in an imager. Transfer the offsets to the spectrograph. Adjust the rotator so the slit points along the tail axis. Start the sequence while the target is still in place. Repeat when winds or flexure move the image. On a quiet prograde comet, the timing is easy. On Atlas, minutes matter. Teams rehearse the sequence with fast asteroids so the muscle memory is ready. Radio arrays do not worry about glare, but they do worry about coherence. The Very Large Array fields 27 dishes across the New Mexico plains. Each antenna tracks a slightly different sky patch because of geometry. The correlator must align phases down to fractions of a wavelength. For a moving target, the delay model changes constantly. Engineers load a non-sidereal schedule that updates pointing and delay tables every few seconds. They set frequencies that avoid solar radio bursts when the comet sits near the sun in angle. They also define a short cadence by default, in case a pickup ion wave lights up without warning. Hubble and Webb face strict limits near the sun, but both can contribute during safe angles. Hubble's fine guidance sensors must lock on guide stars that are not too bright and not too close to the sun. Fast-moving objects complicate guide star selection because the guide loop has to predict drift. The cure is scheduling the shortest viable exposures and bundling them into visits with minimal overhead. Hubble can track non-sidereal targets when the rate sits under a software limit. If the comet exceeds that rate near perihelion, Hubble waits for calmer days on either side. Webb has different constraints. The sun shield must always face the sun. The telescope cannot point too close to the sun or Earth and still stay cold. Even within allowed angles, a moving target stresses the pointing solution. Webb supports moving target tracking within a defined speed window. It can hold a comet steady if the rate is slow enough. For Atlas, that window opens in the weeks before and after the blackout. Webb can then deliver infrared spectra that isolate carbon dioxide bands and faint water lines under low background. Those data anchor the chemistry story while ground sites watch the tail. Coronagraphs on solar missions add context when optical astronomy blinks. They block the bright solar disk and reveal the near-solar environment. A long ion tail can creep into those fields. When it does, even a coarse outline holds value. It can show a sudden tail kink at the moment a coronal mass ejection passes. That timing ties the comet directly to solar drivers rather than to guesswork. Solar wind monitors upstream of Earth add another timing layer. They measure field polarity and pressure hours before those conditions reach the comet's heliolongitude. Operators can then plan extra cadence around predicted current sheet crossings. The United States radio community supplements the VLA with the Green Bank Telescope and university arrays. They can watch low-frequency regimes where pickup waves sing loudest. Coordinating those instruments takes a shared clock and a lean protocol for alerts. A short daily bulletin suffices. It lists predicted rates, recent tail angles, and any solar wind warnings. Each facility decides whether it can squeeze a short dynamic block into the day. The goal is to lower overhead and decision friction. The physics will not wait while a committee votes. Software is as critical as glass. A robust stacking pipeline can save a marginal night. It must accept images from many cameras and still produce consistent outputs. Apertures should be defined in kilometers at the comet, not in arcs, seconds on the sky. Tail axes should be measured relative to the sun vector and the predicted field. Metadata must include non-sidereal rates, phase angles, and exposure timing to the second. Many teams already use such standards. During a fast campaign, consistency makes the difference between a movie you can read and a folder of pretty pictures. Consider a technical vignette from the Southwest. A 1.5-meter telescope at Kitt Peak runs a night near elongation minimum. The team programs a script with 1-second exposures in a narrowband filter centered on a carbon dioxide proxy line. Tracking runs at the comet's rate with a guide box that updates 6 times per second. After 2 minutes, the script pauses and slews 5 arc minutes to a blank field for sky frames. It then returns to the comet for another burst. While the sequence runs, a second computer stacks the first burst and estimates tail axis and standoff distance. Those numbers go into the next morning bulletin. By dawn, the radio group has aligned their logs to those timestamps and finds a matching change in wave power. The loop completes in less than 12 hours. Now, a scene from a backyard in New Mexico. An amateur runs an 8-inch reflector on a sturdy mount. The camera is cooled. The target sits low in the evening glow. Short 3-second shots line up in the comet frame. The software measures a fixed aperture, brightness that can be compared night to night. The observer uploads images and the small photometry table to a shared archive. Their sky is suburban. The data are still useful. Dozens of similar stations across the country create a living light curve that professionals can trust. Scheduling is the hidden art. Every major U.S. observatory keeps a queue of targets of opportunity. These are short requests that interrupt the planned night when a trigger arrives. For Atlas, triggers include predicted current sheet crossings, CME impacts, and Mars parallax of windows. The key is clarity. If the rules are clear, staff can switch modes without debate. A 30-minute slot is small for a big telescope and huge for a fast comet. When the night assistant knows the script and the thresholds, the slot appears on time. Star trailing subtraction has improved enough to make aesthetic choices scientific. The algorithm can smooth trails without eating comet structure. It can recover faint streamers that curl off the main tail. It works best when the field is rich and the mount's drift is well characterized. Teams test on dense star fields months in advance. They feed in artificial comets to check that the code does not invent features. Those dry runs reduce doubt during the rush. Burst imaging flirts with detector limits. Some sensors remember bright sources for minutes. Persistence can leave ghosts that mask real detail. Operators plan around this by avoiding bright stars in the path and by adding short dark sequences between slews. They also keep mounts thermally stable to avoid tip-tilt changes that smear the fixed pattern. The checklists look fussy, but they pay off when the comet sits within a few degrees of the sun. Mars offers a rare 2-point anchor. When Mars orbiters image the same structures as Earth telescopes, parallax unlocks true distances. Teams schedule near simultaneous shots with timestamps to the second. They then measure a kink that moves along the tail in both frames. The horizontal shift between viewpoints yields the kink's actual position in space. Its speed follows from frames minutes apart. Those two numbers test reconnection models more strongly than a single view ever could. Citizen science links the gaps between big campaigns. The American Association of Variable Star Observers hosts tools for comet photometry. Community forums share finder charts and recommended exposure settings. Instructors at community colleges turn the campaign into a class project. Students learn to label frames with UT times and to report magnitudes with error bars. The tone stays careful. Data that miss standards are gently corrected. Good data are praised. The network improves week by week. Hubble and Webb carry a final role beyond their images. Their pointing tables anchor time. When Hubble publishes a scheduled visit window, ground teams can plan around it. When Webb posts a safe angle period, infrared observers on Earth pick their nights to match. Shared calendars reduce duplication and cover the nights that matter most. Small telescopes slot into the days between flagship sessions, filling cadence holes. A separate team tends the ephemerides. As the comet brightens, centroiding gets tricky. The inner coma is not a point. It's not a asymmetric jets can pull the measured center off the true nucleus. The team uses models that fit a point spread function plus a shallow halo. They cross-check with radar if a ping is possible. They adjust the ephemeris as needed and publish updates nightly. If they fall behind, everyone's guiding degrades. When they keep pace, the whole chain stays sharp. Radio teams plan for bad days, not just good ones. They define backup bands when solar noise rises. They set thresholds for switching modes. If the sun flares, they log the event and keep recording with a different setup. That discipline keeps a time series intact through chaos. It also means that the inevitable bad nights do not break the story. There is always usable signal if you know where to look. In the background, data centers absorb the load. Pipelines convert raw frames to calibrated images by morning. A simple summary drops into the shared bulletin. Tail axis angle, standoff distance, proxy, gas output in a standard aperture, each with an uncertainty and a timestamp. The summary is readable to a layperson, yet precise enough for a modeler. That blend keeps the campaign honest. Engineers see this as a systems problem. Mounts, cameras, software, schedules, and people must align under changing constraints. The comet sets the clock. The sun sets the glare. The earth sets the weather. We adapt. We script. We practice. Then we trust the script and the people who run it. When it works, the relay moves with grace, and the data flow like a single patient instrument. All that effort prepares us for the next question, which is how activity around a small, fast comet can ripple through a larger space and touch tools and services we use every day. Space weather is not a movie prop. It is a real environment that pushes on real systems. A carbon dioxide-rich comet adds structure to that environment by painting the solar wind with extra ions and dust. Atlas will not flip a switch on Earth by itself. It can, however, mark when conditions peak and help us time the pushes that matter. The right stance is sober, not scared. Start with timing signals. GPS satellites broadcast precise clocks. Your phone and truck and survey rig depend on those clocks. Space weather disturbs the ionosphere, the ionized layer that those signals cross. During strong events, the ionosphere turns lumpy. Radio waves bend and slow by uneven amounts. Receivers see jitter and occasional dropouts. The fix is known. Aviation and shipping use dual-frequency receivers that correct for delay. Survey crews add local reference stations that scrub errors. The risk rises when a flare or a coronal mass ejection lifts electron density fast. A bright, active comet during solar maximum can help predict those windows. If Atlas shows an ion tail twist at a current sheet crossing, controllers know to expect shifts in a few hours as the same structure sweeps our longitude. Air traffic cares about radio, not just GPS. Long-range flights rely on high-frequency voice links over oceans and poles. Those bands ride the ionosphere at night like a sky mirror. Space weather changes that mirror. Sometimes it goes black. Controllers move traffic to different routes in different bands. Airlines plan polar detours when radiation levels climb. These steps have cost and delay, but protect crews and passengers. The United States aviation system has playbooks for all of this. The new part is cadence. Atlas can add an extra clock tick on days when the ion tail jumps. That cue is not a warning of harm. It is a nudge to check the dashboard more often. Communication satellites work above the ionosphere, but still live in space weather. Charged particles charge surfaces. Surfaces discharge in tiny arcs. Electronics feel those arcs as glitches. Operators see bit flips and brief resets. They can switch to safe modes and change pointing to reduce heating. They can also time software updates to calmer hours. A comet tail near perihelion might radiate at radio frequencies as pickup ions stir waves. Arrays on Earth can hear the pattern. When matched to solar wind monitors, those patterns give operators a rhythm to trust. That trust improves decisions during a busy month. Power grids face a slower, deeper risk. Geomagnetic storms induce currents in long conductors. High voltage lines stretch for hundreds of miles. Those lines collect small voltages end to end. The currents flow into transformers. The extra heat and harmonic stress insulation. A severe storm can force operators to shed load or trip equipment. The United States has seen versions of this story during past cycles. The defense is vigilance and margin. Operators reduce transfers, cool oil, and watch reactive power. They make grids slightly looser for a few hours. A well-timed loose grid rides out a shock. A tight grid strains. Atlas does not cause the storm that matters here. The sun does. The comet gives a timing reference and a laboratory to test models that tie solar events to ground risk. Pipeline operators also watch the same charts. Long steel pipes pick up induced voltages. Corrosion control systems must adjust. Rail operators keep an eye on signals that rely on long wires and ground references. None of these sectors need panic. They need honest forecasts with uncertainty bars and short updates during active days. A clear sentence that reads the wind helps. The presence of a structured ion tail near a current sheet crossing helps time the sentence. A fair concern is radio interference tied to the comet itself. The bright nucleus and its plasma do not beam at communications bands with enough power to matter at Earth. The radio signatures arrays will chase are faint. They are easier to hear with large dishes and clean processing. Your phone, your weather radar, and your traffic channel will not notice the comet. They will notice the sun if the sun flares and sends a shock into our magnetic field. That is the difference between causal drivers and helpful markers. The comet helps us read the clock that the sun sets. Air routes over the United States could see small, temporary changes in preferred altitudes if high-frequency conditions degrade. Controllers might favor more satellite links and fewer skybounce paths during active hours. Satellite links depend on GPS time. They work best when receivers see dual frequencies and integrity checks. Those features are common in aviation equipment. They are less common in consumer gear. The message for the public is simple. Navigation in the air will keep its margin. Your car may see a brief map wobble if you drive under trees during a bad hour in October. That wobble will pass. Emergency communications rely on a mix of tools. First responders use VHF and UHF systems that do not reflect off the ionosphere. Those bands are robust during storms. Amateur radio groups operate on lower bands that do reflect. They treat space weather as a field exercise. Some clubs will try to hear the comet tail as a science project. Others will practice message relays when the night sky mirror changes. This is not a threat to public safety. It is a chance to train. Commercial satellites that serve television and internet live in geosynchronous orbit. They see particle storms as prolonged rain. Ground stations adapt by shifting to lower data rates or to higher power for a few hours. Users might notice brief buffering in fringe coverage areas. This is not a nationwide blackout scenario. It is a cloudburst that a seasoned network knows how to ride out. The measure of success is that most people never hear about it. High-latitude states see stronger ground effects. Alaska and the northern tier sit under auroral ovals when storms hit. Induced currents can be larger there. Grid operators in those regions already plan for it. The difference during a month like this is persistence. Storms can arrive in clusters. Margins need recovery time. A well-spaced cadence of alerts helps protect that margin. Here again, the comet adds timing cues. When the ion tail kinks in the predicted window, it confirms a boundary crossing underway. There are limits to what a comet tells us. It does not make a weak shock strong. It does not create new energy in the wind. It exposes structure at a location in space where we can see it. With that structure, we learn when to expect field polarity changes and pressure rises. We tie those changes to responses at Earth with less guesswork. The process feels like watching a river gauge upstream of a town. The gauge does not cause a flood. It buys you time. A bold idea has stirred attention. Some see hints that electromagnetic effects near the comet could couple across very large distances. That claim would widen the zone of care. It would also push against what we know of dissipation in the solar wind. The safe reading today is conservative. Connectivity in space follows magnetic field lines and pressure fronts. Coupling fades with distance and with mismatched conditions. Coordinated changes would need a clear path and a clear timing chain. If evidence builds, we will update the story. Until then, system-wide coupling from a comet sits in the box marked speculative. Another topic that deserves clean language is radiation dose. Air crews on high-latitude routes can see small increases during solar particle events. Airlines track this and adjust exposure by route. A comet does not add to that dose. It does not accelerate particles to energies that reach aircraft. The sun does. The comet clocks the solar wind and traces the magnetic field in ways that help planners schedule smart detours. Spacecraft in deep space may offer surprise correlations. Missions like Parker Solar Probe and Solar Orbiter sample fields and particles near the sun. If their logs show changes that align with events at the comet by traced field lines, modelers will learn a lot. Those alignments would not imply the comet drives the sun. They would reflect how disturbances travel along the same large-scale network. That network is the heliosphere. The comet is a tracer in that network, not a controller. Satellite autonomy has improved in the last decade. Many platforms can detect high particle flux and switch to safe configurations on their own. They power down non-essential systems and harden critical paths. The decision thresholds are tuned to avoid false trips. During a month, with a bright, structured comet, operators can retune thresholds by a notch and restore them later. That small change can cut nuisance resets without blunting protection. It works best with fresh context, which is what the daily cadence provides. The United States grid has made changes since past storms. There are new standards for transformer resilience, for monitoring, and for operator training. These measures reduce worst-case scenarios and improve recovery. There is no switch that eliminates induced currents. There is a set of habits that keep them within safe bounds. Those habits are closer to craft than code. They depend on people who can read a one-line summary and act with confidence. Adding a comet to the toolbox is not a distraction. It is another thermometer in the room. Space weather forecasting blends physics and statistics. Models use solar images, coronagraph frames, and in situ monitors to predict arrival times and intensities. The comet adds an extra probe in the flow. It gives modelers a check on field direction and ion pickup near a moving marker. That check can shave hours of uncertainty from some forecasts. The goal is not to chase perfect foresight. It is to make useful promises with honest ranges. A county emergency manager needs to know if a window runs 2 hours or 12. A grid operator needs to know if a margin is slim or wide. A flight dispatcher needs to know if a polar route is discouraged or fine. Public communication should stay plain. If the sun launches a big ejection, say so. If the comet shows a tail cut at the expected time, say it confirms the crossing. If GPS sees glitches, say they will pass and that dual frequency gear will cope. Avoid dressing small shifts as crises. Avoid downplaying real storms as routine. The tone should match the evidence and the stakes. This is not a season for hype or for denial. Households do not need to stock special gear for a comet month. Basic preparedness remains basic. Keep phones charged. Know where a flashlight is. Expect some aurora alerts in northern states. Look up when skies are clear. If you are a hobbyist with a shortwave radio, enjoy the changing skip. If you fly, trust the crews and controllers. If you work on a line crew or in a control room, you already know the drill. The single metaphor for this section is a weekend traffic pattern. The sun is the interstate. Weather fronts are lane closures. The comet is the digital sign that shows how fast cars move at a point ahead. It does not set the speed, it reports it. Good drivers use the sign to merge sooner and breathe easier. They still keep both hands on the wheel. This system view brings us to a natural question about how often such visitors pass and why many go unseen, which is where the interstellar population and our blind spots take the stage. A bright, active comet like Atlas is the exception we notice, not the rule we miss. Interstellar space likely carries countless small bodies that never advertise themselves. They coast through the inner system as dark shapes, reflect little sunlight, and shed no gas. Telescopes scan huge swaths of sky each night, but they still catch only a sliver of what passes by. The math of that blind spot matters if we want to place ATLAS in its true crowd. Begin with the simple constraint of brightness. Surveys find what rises above the background in a short exposure. If an object does not outgas, it stays close to the reflectivity of bare rock. Many such bodies are charcoal dark. At a distance of 1 astronomical unit, a football field-sized rock can be fainter than a dim star in a suburban sky. Even with a large mirror and a sensitive camera, that rock must be in the right place, at the right time, at the right angle. An active comet lifts its own streetlight. Gas and dust spread sunlight over a large area and boost the signal. Carbon dioxide does that trick earlier and farther than water. Atlas benefits from that physics. A look-alike without outgassing would pass unnoticed. Speed shapes the search. Interstellar visitors move fast. Atlas will cross the inner system at tens of kilometers per second, roughly dozens of miles per second. That speed blurs a faint dot during a long exposure. Surveys respond with shorter frames, but shorter frames mean fewer photons. The pipeline must choose aggressive track rates to follow the motion, and that choice raises false alarms from streaking noise. The safest settings reduce error but throw away some targets. The result is simple. We favor bright, active travelers over dark, quiet ones. The sample we study is not the sample that exists. Geometry trims the list again. A telescope cannot point everywhere. Sun avoidance angles keep optics safe. Mountain shadows and weather cut nights short. The moon washes out faint trails for a week each month. Twilight areas near the sun, where many fast movers lurk, are hard to search with depth. Special twilight surveys help, yet they trade sky coverage for cadence. The southern hemisphere sees zones the northern hemisphere misses, and vice versa. Gaps pile up across time and space. Visitors can slip through those gaps without leaving a trace. Cadence drives another bias. A survey might return to the same field every few nights. A fast object can move out of the field before the next pass. Linking detections across nights requires a chain of sightings with a compatible speed and direction. If an object is faint on the first night and hidden by weather on the third, the chain breaks. The pipeline drops the candidate. An active comet builds its own cushion by staying bright long enough to survive gaps. An inactive object has no cushion. It appears once and vanishes into the noise. We also bias towards certain sizes. Cameras have sweet spots. Too small, and an object never rises above the noise. Too large, and it moves slowly enough to look like a local asteroid. We flag many slow movers as near-Earth objects and treat them as residents until their path proves otherwise. The rare fast mover has to be obvious for the software to elevate it quickly. That pipeline choice keeps false positives low. It also filters out marginal interstellar candidates. Atlas draws attention because its chemistry and scale help it beat those filters. A carbon dioxide to water ratio near 8:1 lifts activity early. The coma expands to hundreds of thousands of kilometers, on the order of 200,000 miles or more, while the nucleus stays below 5.6 kilometers, about 3.5 miles. The result is an easy target for detection algorithms that look for moving, fuzzy patches. If the nucleus carried water near the surface and carbon dioxide deep, the same body might sleep until much closer to the sun. It would wake late, spend less time in favorable angles, and risk discovery only when glare is worst. The object would be the same mass and speed, but to our surveys, it would be a ghost. A single metaphor can help frame the bias. Picture a night boat working a huge lake with a small net and a bright lure. Fish that rise to the light end up in the net. Fish that cruise deep or ignore the glow slide by under the keel. The catch tells you something about the lake, but not the full story. You could think the lake holds only surface feeders. You would be wrong. The right lesson is to remember the net, the lure, and the method. Our surveys are that boat. Atlas swims in the slice of the lake that we skim well. What does this mean for population counts? Raw counts of detected interstellar objects represent a floor, not a full inventory. To approach the true number, we need to fold in the chance that an object with certain traits would have been seen. That means modeling the sky coverage, the depth, the motion cuts, and the geometry for each night. It means simulating millions of fake objects with different sizes, speeds, and albedos. It means letting the fake sky run through the real pipeline. The fraction that comes out tells us how blind we are. When teams do this with local asteroids, the bias corrections can be factors of 10. For interstellar bodies, the factors may be larger because the priors on speed and size are wider. The concept of a dark population follows from this bias. Dark does not mean invisible in principle. It means inactive in gas and low in albedo. Infrared telescopes can sometimes catch such bodies if they are warm enough to glow against the cold sky. In practice, small interstellar rocks stay very cold. Their thermal signature is weak. Current infrared surveys favor larger, closer targets. That leaves a large swath of space where inactive visitors roam unseen. We assume they exist because the physics of planet formation suggests a robust ejection of debris from young systems. Those ejections include ice-rich bodies and dry rocks. The dormant half slips under our current nets. The chemical diversity on display with ATLAS hints at what the dark population could carry. A carbon dioxide-rich mantle near the surface implies a formation zone beyond the water snow line in a protoplanetary disk. Different stars build disks with different temperature profiles and chemical gradients. Some disks may place the carbon dioxide snow line far from the star. Others may mix ices more deeply with refractory material. Ejection can occur at many stages. Some bodies leave early, while ices are fresh and layered. Others leave late, after heating and impacts have altered the crust. Each body becomes a time capsule for its birth zone and its later processing. The capsules we see are biased toward those that vent. The capsules we miss could hold different stories. Astrobiology cares about this bias. Models of how planets gain volatiles often invoke comets and small bodies as delivery trucks. If the trucks come in many chemistries, the delivered atmospheres and oceans will vary widely. Carbon dioxide heavy bodies might seed early atmospheres with greenhouse gases that change the thermal path of young worlds. Water-heavy bodies might build oceans more directly. Organic-rich crusts might carry complex molecules that prime prebiotic chemistry. If our sample favors one end member, our expectations about habitability follow that skew. The cure is to widen the sample with new tools and clever strategies. Planet formation theory also needs a broader set of witnesses. The positions of snow lines, the efficiency of mixing, and the timescales of disk evolution all leave marks in small bodies. If interstellar space is full of such markers, and we see only the loudest, we risk tuning models to the wrong details. Atlas pushes us to ask how many bodies share its carbon dioxide dominance. Are we seeing a common product of outer disk chemistry, or a rare one? The answer depends on finding more, not on staring longer at one. How can we change the bias? Two paths exist. One path is deeper and wider visible searches that look near the sun in twilight, with fast cameras and smart track rates. These hunts trade ease for reach. They need careful background subtraction and quick follow-up. They also need a pipeline that forgives odd motions for a night or two. The second path is thermal infrared at high cadence. A warm, dark rock gives off a small glow, even if it reflects little light. Space-based infrared surveys designed for moving objects could lift the dark population into view. Both paths cost money and time. Both are within reach if we decide they matter. Coordination improves yield. A faint streak caught by a twilight camera can trigger radio arrays to listen along the predicted path. A thermal blip can ask an optical telescope to scan a tight patch of sky with non-sidereal rates. Amateur and professional networks can share quick finder charts and simple ephemerids that do not overwhelm. The key is speed, and an active rock will not stay in any one patch long. Reaction time beats raw aperture many nights in a row. The United States landscape can support these strategies. Desert skies in the southwest allow low-altitude twilight work. Midwestern and eastern sites add dense coverage and access to student observers. Hawaii and Puerto Rico provide stable air for infrared and radio. A national culture of amateur astronomy adds hundreds of capable eyes and rigs that can pivot in hours. Small grants and shared software can unify this spread into a flexible net. It will never catch everything. It can catch more. We should calibrate our expectations without cynicism. Even perfect coverage will miss some visitors. Interstellar space is large, and our slice of it is thin and busy. What matters is to know which classes we see well and which we do not. The bias corrections then become honest parts of every plot and conclusion. When someone quotes a rate of interstellar visits per year, the next sentence should state the assumptions about brightness, activity, and geometry. That habit makes the field stronger and the stories truer. There is a human angle here too. We notice what glows. We set our gaze by what returns the most signal for the least effort. That is good craft and good stewardship of time. It is also a lens that needs periodic adjustment. Atlas acts as a reminder. Its early carbon dioxide surge made it easy to see. Its retrograde geometry made it dramatic. Its speed made it urgent. From those traits, we can infer only so much about the unseen fleet. We need patience to build better lures and better nets, and humility to admit what still swims below. As the sample grows, a larger theme emerges. Many of these bodies, active or not, appear to self-organize their near surface and near coma environments in repeatable ways under solar forcing. Vents open and close. Dust charges and flows. Tails twist with field changes. The patterns look like a kind of learned behavior, though there is no mind behind them. That image tempts language we should use with care. It opens a door to a cautious metaphor about evolved matter, a phrase that can help us talk about complex self-organization without stepping beyond the evidence. Evolved matter is a careful phrase, not a claim that rocks can think. It is a way to talk about complex self-organization in a harsh environment without borrowing the language of minds. In this frame, a comet is a small system with many moving parts. Ice changes state. Gas escapes. Dust lifts, charges, and settles. Sunlight adds energy that varies with distance and angle. The solar wind brings magnetic fields and shocks. Out of these pushes and pulls, patterns appear that look coordinated. The point of the metaphor is to keep our focus on physics, while admitting that the physics can arrange itself. Self-organization is common in nature. Hot fluid can roll into convection cells. Snowflakes grow with repeated rules that yield detailed shape. Lightning follows paths of least resistance that build in microseconds. None of these systems has a plan. They respond to gradients and constraints. Comets do the same. They present porous crusts and layered ices to a changing heat lamp and a flowing plasma. The result is jets, shells, and tails that adapt as conditions swing. Evolved matter, in this usage, means matter shaped by history and feedback, not by intent. Why does the idea appeal here? Atlas carries carbon dioxide close to the surface. It vents early and far from the sun. The coma swells to hundreds of thousands of kilometers, while the nucleus stays under 5.6 kilometers across. The ion tail kinks at crossings of the heliospheric current sheet, or HCS. Coronal mass ejections sweep past, and the tail sheds segments. Radio arrays report patterns timed to pick up ion waves. The sequence can look like a system that tunes itself. It might only be a system that reacts quickly along many coupled pathways. The metaphor helps us hold both views while we gather facts. A key feature is memory stored in structure. A comet's crust records past heating and cooling. It holds cracks where gas once flowed. It carries layers where dust fell back and sealed pores. Thermal skin depth defines how far a daily or seasonal heat wave penetrates. That depth in carbon dioxide ice is small, on the order of centimeters, but it adds up over weeks. When Atlas rotates, vent sites come in and out of light. Patches that darkened from past dust shedding heat faster. They will open earlier each day. That is history expressed as a pattern, not as purpose. Feedback loops turn small changes into big ones. If a vent exposes fresh carbon dioxide, gas pours out. Gas drags fines off the surface. The surface darkens and heats. Sublimation rises again. The cycle continues until the mouth sags and chokes. Flow drops, and dust settles back. The patch brightens and cools. Another site takes over. The whole coma shifts shape even if the total gas output barely changes. The pattern looks like control. It is only coupled processes climbing and falling together. The plasma adds another layer of coupling. Photoionization turns neutral gas into ions and electrons. The solar wind picks up those ions and forces them along field lines. The ion tail points away from the sun and can swing with field direction. Dust grains charge by sunlight and by electron impacts. Charged grains respond weakly to fields if they are large. They respond more if they are small. That size spread lets dust sort itself into arcs and fans. A crossing of the HCS flips polarity. The ion tail can twist. A thin current sheet can reconnect. A tail segment can detach and drift. None of these steps needs intention. Together, they create a sequence that looks organized. This is where language matters. If we say the tail chooses a direction, we hide the field flip. If we say the coma talks to the tail, we lose the pickup process. The safer path is to describe the chain with verbs that name actions. Gas vents, dust lifts, ions form, fields drape, tails kink, waves grow, energy converts. These words make the behavior vivid without granting purpose. Evolved matter stays a metaphor for shape over time, not a label for agency. We can ask whether repeated solar encounters could select for certain surface states. Selection here means survival of structures, not survival of individuals. A crust that seals under dust will lose gas more slowly and erode less. It will tend to persist. A crust that fractures into open pits may blow itself smoother and lose volatiles. It will tend to fade. Over many perihelia, survivors would share features that resist loss. The population of surface states would drift. That idea is natural selection of physical traits, not biological evolution. It is plausible. It is not yet measured across interstellar comets. We should mark it as a hypothesis to test when samples grow. What tests could we run? We can compare activity profiles across comets with similar chemistry. If carbon dioxide-rich comets show the same early rise and the same tail behavior at HCS crossings, we have a pattern. If they differ in ways tied to rotation rate or nucleus size, we have parameters to track. We can watch how the ratio of carbon dioxide to water changes after perihelion. A crust that closes vents will show a faster drop in carbon dioxide output. A crust that stays open will hold the ratio longer. These are predictions that do not require new physics. They require cadence and careful calibration. The radio story fits the same approach. Pickup ion waves should appear at frequencies set by basic parameters. If arrays across the United States hear those bands rise and fall in step with tail kinks, we gain confidence that the waves trace the draped field. If radio patterns repeat across similar events, the case for self-organized plasma cycles grows. If the patterns do not repeat, the case weakens. We label the current reading as observation with several viable models. We reserve stronger claims for later. Structured emissions tempt bolder leaps. Some groups have suggested that modulation patterns hint at information processing. That phrase moves fast. It needs restraint. A plasma can store and release energy in regular ways without encoding messages. It can build standing waves and beat notes that sound organized. The cautious reading is simple. The comet tail is a resonant structure. It rings when driven by the solar wind. The ring is science, not speech. Anything beyond that is speculation and needs clear evidence and a mechanism. The single metaphor for this section is a stadium crowd that starts the wave. No captain commands the wave. A handful of fans stand. Their neighbors copy them. The crest travels around the seats. The shape emerges from local rules and attention. The crowd has no plan, yet the motion looks designed. It repeats when conditions are right. Change the music or the mood, and it fades. The comet's coma and tail can act like that crowd. Local rules and inputs create larger order that looks intentional. We enjoy the order. We analyze the rules. We should also examine our bias as observers. Humans love patterns. We link events that occur together, even when a third factor drives both. The sun sets the common clock. The HCS flips field direction on a schedule. Coronal mass ejections throw pressure pulses that pass many longitudes. If the tail kinks and a radio pattern rises, both could share a cause. That is a clean reading. It is not a hidden conversation. The cure for bias is timing chains that run through multiple sensors. A kink seen from Mars and from Earth at the same instant is real. A radio surge that aligns with a magnetic flip seen by a spacecraft adds weight. The more links, the fewer leaps. Laboratory work can ground these ideas. Cold plasmas with dust can form waves and voids on benchtops. Jets in vacuum chambers can carve pits in mixtures of ice and dust. Extreme ultraviolet lamps can drive photonization in small gas flows. None of these rigs matches a comet scale. They do match small parts of the process. They test the rules that local patches follow. Then models can scale those rules up with care. If a bench result never appears in the sky, the model that depends on it must change. We must also keep the door open to surprises. Atlas is fast, carbon dioxide rich, and retrograde. Those traits already place it at the edge of our experience. It will cross the HCS at solar maximum and meet several coronal mass ejections. The combination is rare. It could reveal couplings we have not mapped. An open mind does not mean an open season for claims. It means we accept that some links in the chain might need new terms when data force them in. Evolved matter can guide our questions without blurring our judgment. If structure stores memory, we look for hysteresis. If feedback drives bursts, we look for thresholds and jumps, not smooth ramps. If local rules build global order, we search for repeatable shapes and phase relationships. Each of these searches uses standard tools. Photometry for light curves, polarimetry for dust grain alignment, spectroscopy for gas ratios, radio timing for wave trains, magnetometry for field direction. We do not need new senses. We need coordination and patience. The metaphor also helps us communicate. The United States audience lives with complex systems. Power grids balance demand and supply. Phone networks reroute around faults. Road traffic forms waves with no one in charge. These systems work because local rules and feedback loops shape the flow. They also fail in ways that spread fast. A comet's coma is smaller but follows the same logic. Local physics, repeated many times, builds large structure that changes with context. Calling that structure evolved matter keeps our words honest and our curiosity sharp. How do we avoid the trap of agency? We use clear labels when we speculate. We tie every fresh claim to a measurement that can confirm or deny it. We keep cause and effect in order and state what could break that order. We declare our priors and update them. We build ensembles for models and show their spread. We resist the urge to fill silence with stories. The comet does not care if we find meaning. It will fly its path and shed its gas. Our task is to record and infer with care. If we ever do find a signature that cannot fit within natural self-organization, it will stand not on tone but on stubborn data. It will be repeatable. It will resist alternative models. It will show a mechanism or force one into being. That bar is high on purpose. We have much to learn within the realm of plasma physics, thermal physics, and material science. We should climb that hill before we hunt for taller peaks. Evolved matter, then, is a map legend, not a destination. It reminds us that structure comes from history and feedback. It keeps us from dismissing order as coincidence while also steering us away from premature claims. It protects the science from hype and holds the thriller tone to the pace of evidence. Used well, it helps us explain why a small body can show large, coherent behavior during a month of strong forcing. The next step is to ask which measurements in the coming weeks would tighten the most knots in this story, and that turns our focus to the final observation window and what we stand to learn if we use it well. The last weeks before and after October 29th are a harvest window. The crop is information, the weather is solar maximum, and the field is a thin ribbon of space that the comet will cross only once. If we move on time and in order, we can bring in data that reshape how we talk about chemistry, plasma, and models for years. If we slip, the wind takes the grain, and the chance is gone. The plan is simple to say and hard to execute. It asks us to gather a few clean numbers, many times, from many places, and to tie them together with clocks that agree to the second. Chemistry comes first because it anchors every other story. We need the ratio of carbon dioxide to water as a function of time, not as a single headline number. Infrared spectra before the glare, and again in December, can track how the 8-to-1 balance evolves as vents open and close. If the ratio falls quickly after perihelion, the surface likely seals under fallback dust. If it stays high, active patches may stay open longer than expected. Narrowband imaging helps by isolating gas bands near the inner coma, where mixing is minimal. A steady cadence of short exposures converts a rough curve into a readable log. When those curves sit next to the rotation period, we can tell which spikes are geometry and which are genuine bursts. Dust sits beside gas as the second pillar. Polarimetry can reveal grain sizes and how they change during heating. If fine grains dominate near perihelion and coarsen later, that pattern speaks to how jets sort and charge particles. Phase angle corrections must be applied with care. because forward scattering near the sun can make dust look richer than it is. The December return offers an honest look when the geometry calms. Photometry in fixed kilometer apertures, repeated night after night by many sites, will map the fading tail without mixing sky brightness into the signal. Nucleus constraints arrive in pieces. Hubble or ground adaptive optics can search for a hard central core in moments when the inner coma thins. Radar, if signal allows, can bound size and spin. Even without a crisp image, a rotation period found in light curves will clarify how jets sweep space. A slow roll means long exposures on a small set of active patches. A fast roll smears features and spreads gas evenly. Either case informs heat flow in a carbon dioxide mantle and lifts model degeneracies. Plasma behavior is the heart of the month. We need standoff distance, the gap between the nucleus and the ion pileup, measured as often as possible. That single number tells us how solar pressure and gas output balance. A sudden drop marks a shock, or a coronal mass ejection. A rise marks a lull or a shift in venting. The tail axis angle relative to the sun vector shows the draped field direction. When the comet crosses the heliospheric current sheet, or HCS, the axis should twist in a predictable swing. If the swing deviates, we learn about local turbulence and Hall effects that simple magnetohydrodynamics, or MHD, smooths away. Tail disconnections carry extra weight. If a segment breaks off during a crossing or a pressure spike, its timing and speed constrain reconnection rates. 2 vantage points, Earth and Mars, make that constraint sharp. When both sides see the same kink at the same time, parallax fixes the kink's location and motion in space. With motion known, a reconnection model cannot hide behind unknown geometry. It must match the pace. That is how bench physics, hybrid codes, and MHD patches meet a real scoreboard. Radio signatures are a third plasma probe. Pickup ion waves should sing at frequencies set by the local field and by the mass of ions created from carbon dioxide. Arrays in New Mexico and West Virginia can listen across daily windows. If power rises at the same time the tail axis swings, the case for a simple driver strengthens. If radio patterns drift independent of visible changes, we look closer at waves, dispersion, and local plasma beta. The goal is not to chase novelty. It is to tie specific features to specific mechanisms and to show which ones repeat. X-ray and ultraviolet glow can round out the picture. Charge exchange between solar wind ions and neutral gas leaves a soft X-ray signature. A rise in X-ray emission during a coronal mass ejection would confirm that fresh ions are hitting dense gas near the coma. That confirmation matters because optics can saturate while X-ray counts climb in a useful way. The same logic holds for ultraviolet lines that trace water fragments. Each band is a different window into the same room. We want them all open when the house shakes. System context protects us from fooling ourselves. Solar wind monitors near Earth record field polarity and pressure hours before those conditions pass the comet's longitude. Simple ballistic mapping can predict when the same structures will reach the target region. When a current sheet is due, we plan extra cadence. When pressure rises, we watch standoff distance more often. If a disconnection happens outside those windows, we ask if local processes on the nucleus created the timing. If it happens inside, we can attribute with more confidence. Either outcome teaches us which knobs matter most. A human layer threads through every number. The United States network of professional observatories and citizen rigs must keep cadence even when titles and budgets change. Success looks boring up close. It is the same short exposure, repeated at the same clock times across many nights. It is the same log field filled with UT stamps, phase angles, and aperture sizes. It is the same daily bulletin with standoff distance and tail angle, written in plain language and sent on time. Craft beats drama in a harvest window. Models advance only as fast as inputs do. The best use of this month is to lock down a handful of boundary conditions that any credible simulation must honor. Gas production as a function of time is one. Standoff distance and tail angle through multiple HCS crossings is another. Disconnection event timing and length is a third. Radio wave frequencies at known intervals is a fourth. With those pins in the map, MHD can draw broad flows, and hybrid patches can set reconnection pace without guessing at invisible parameters. Ensembles can then reveal uncertainty bands that we can quote with a straight face. We can also use this window to calibrate subgrid terms that weather the code cannot resolve. If we see that disconnections always lag pressure spikes by a few minutes, we can tune effective resistivity to reproduce that lag. If charged dust arcs appear at specific phase angles and not at others, we can update simple dust charge laws. These are not cosmetic tweaks. They are the way applied physics grows more predictive. Speculation has a small place if the guardrails are sturdy. Structured radio patterns have raised eyebrows. The safe test is whether those patterns scale with field strength and ion species as pickup theory demands. If they do, we accept a natural resonance. If they do not, we list alternatives in order of plausibility, starting with measurement artifacts and moving outward only as evidence compels. The word speculation should appear in any sentence that steps beyond tested mechanism. The payoff for restraint is trust when we finally do report something strange. A parallel benefit will touch operations. Air traffic rules for polar links, satellite safe mode thresholds, grid margin steps, and GPS integrity flags all depend on forecasts that handle timing and intensity well. A comet that acts as a tracer at multiple longitudes can sharpen those forecasts by removing an hour here and an hour there from arrival ranges. We should measure how often such sharpening helps real decisions, not as a press claim, but as a sober after-action note. If the answer is seldom, we adjust expectations. If the answer is often, we add tracer logic to future playbooks. What would failure look like? It would not be a quiet sky. It would be a flurry of images without clocks. It would be stacks without phase angle corrections. It would be radios listening at the wrong bands and telescopes pointing at the wrong hour. It would be models tuned after the fact to match pictures with hand-picked parameters. Failure would look busy. It would only feel useful until later, when we try to compare notes and find that times and units do not match. The cure is discipline now, not regret in winter. What would success look like? It would be a Mars parallax sequence that fixes the three-dimensional position of a tail kink. It would be a standoff distance curve that rises and falls in step with recorded pressure pulses. It would be a CO2 to H2O ratio that tells a clean story about vents, sealing, and opening. It would be a radio band that grows and fades with predictable links to field strength. It would be a small set of numbers that any model must hit to be taken seriously. It would be a December recovery that shows how the system heals after the hard days. It would be a public archive with plain labels so that a student in a year can reproduce a plot without guessing at hidden steps. As the harvest window opens, we should also widen the circle. Community colleges, high schools with observatories, and amateur clubs can adopt small but critical roles. A daily photometry run at the same hour adds weight to a light curve. A short radio log that marks noise and local interference helps clean a larger data set. A careful note that clouds arrived at 1954 UT can save a misreading weeks later. This is not busy work. It is how a national network turns into a single, coherent instrument. The single metaphor for this section is harvest, because it places urgency in the right place. Crops do not yield to speeches or headlines. They yield to rows walked, bins filled, and weather watched. A good harvest is 1,000 small actions done on time. A great harvest is the same work coordinated across fields so that trucks and silos never sit idle. The comet has set the date. The sun has set the weather. Our job is to move. By the time the glare fades and the tail lengthens in a darker December sky, we will know whether we caught what mattered. And that is the moment to return to the countdown itself and the quiet reasons this work is worth doing. On a late October clock, the sun, the wind, and a small, ancient body will run a live test of our physics and our poise. The date is circled, October 29th. By then, we will have watched a retrograde traveler cross lanes at highway speed, seen carbon dioxide drive a coma the size of a planet's daylit face, and traced a tail that answers to the heliospheric current sheet. None of it asks us to be alarmed. All of it asks us to pay attention. This month is not a spectacle we consume. It is a lab we build together. A telescope in Hawaii, a dish in New Mexico, an 8-inch rig behind a garage in Ohio, a spectrograph slot at Kitt Peak, a cadence note at Green Bank. Each piece adds one clean measure at the right time. From those pieces, we shape a record that lets models face facts and lets operations make better calls. The reward is simple. Tomorrow's forecasts improve. Next year's tools grow sharper. The story of small bodies crossing star systems becomes less guesswork and more knowledge. When the glare eases in December and Atlas slides into a darker sky, we will count what we learned. Some answers will confirm the rules we trust. Some will stretch those rules without breaking them. A few will point to gaps we can now name. That is a good outcome. The universe stays wide. Our reach grows by a step. The countdown ends, and the work becomes memory, data, and a quiet proof that patience, craft, and cooperation still turn distant light into understanding.